My name is Austen Gabrielpillai. I am finishing up my time as a master's student at the CUNY Graduate Center. I'll be starting at Columbia in a month or so as a PhD student, very wild to say. And I've been working with Sapphire under Raj Pandya, Ari Mahler, Rachel Somerville as part of my time at CUNY. And so today I'm going to be talking to you about how we have been extending Sapphire to model both satellite and host galaxy coevolution, as well as applications to the high redshift universe. So this is a bit of a two-topic talk, and so might as well start going down this blue rabbit hole over here, right, which is the crux of my master's thesis. And so Raj has already done the nitty-gritty of explaining Sapphire, so I could just jump into the problem. And as he's addressed, Sapphire, great model it is, does not currently have satellite galaxies. And so it's been an effort and endeavor on our part to add satellites so that they can be co-evolved with their host galaxy. And so we've broken this up into a two-part problem. This first phase, which I'm describing here, is to model the surviving satellite population so that we can understand what physics we need to be adding to get our surviving satellites to look relatively right to observations. And so in this first phase, we've added coevolution with the host galaxy. We've added some size profiles so that way we can implement additional physics later on. And then we've also added starvation, metallicity pre-enrichment, and then ISM and CGM gas ram pressure stripping. And so to do this, we have to use a set of merger trees. And originally, we were working with TNG50, but then we were finding that we were losing our satellites around 0.5 RVR, so not that great for trying to model surviving physics. So we are using these merger trees, which Ethan has already outlined, as well as other individuals, being from the Symphony zoom-in suite. So specifically, we are using Symphony Milky Way, as well as Milky Way Est. And the great part about these trees is that we could follow down subhalo invol position down to around 0.1 RVR of the host. So this gives us about, giving their mass resolution limits, about 3,000 or so satellites that we could be playing with. And so to benchmark how well we're doing with our model, we're doing a number of different comparisons. First, we're comparing to our fiducial model, where we have none of the additional physics, and then we are doing, we are also comparing with our updated model with satellites, which we're calling our RPS, standing for ram pressure stripping, because that's the most dominant effect that we've seen. And so to start off and kick it off with this comparison is that we are looking at the cumulative stellar mass function of all of our different systems running on Milky Way Est and Symphony Milky Way. And from it's a little hard to see on this plot right here, right? But between our medians for this distribution, which are the lines, and then the 1684 percentile, which is a shaded region, there is some minor effect by adding our additional physics. You could see that this orange line, which is our updated model, shifts slightly to the left, right? But you don't see that big an effect in the cumulative stellar mass function. We are overall, though, still matching the Milky Way pretty nicely up until about the reported completion limit. So we're not affecting cumulative stellar mass function too much, but we do see an effect when we're looking at the star formation history of our satellite galaxies. So over here, we're looking at T50, how long it took a galaxy to assemble 50% of its stellar mass, versus T90, how long it took for it to assemble 90%. And what we can see here is by adding this additional physics, we don't see that much of a difference in T50. But when we look at T90, you're shifting from this median peak around like 5, 6-ish gigayears ago to now 9 gigayears ago. So our galaxies in our sample, by adding ram pressure stripping, are quenching a lot faster. And this also then opens the door for us to be starting playing with parameters such as the ones governing reionization. So that way we can better match the Milky Way T50, T90 observations that you also see on this plot over here. We've also done this comparison when you want to look at the interstellar medium for our galaxies. So we're plotting ISM gas mass versus stellar mass here. And with our base model, the blue, we are not matching the Milky Way at all. So we need ram pressure stripping to better match these Milky Way observations, which for the most part are upper limits. And the Milky Way is great overall. We love it. We live in it. But it is effectively one data point. It's one system, right? So we're also doing comparisons by extending it to extragalactic surveys, being the SAGA and ELV surveys. And this paints now a very interesting picture of these comparisons, where with SAGA, which we're showing in green, we're pretty much matching fairly well to the observations, but then ELS makes it a very more interesting story because you do have these upper limits there, but you do have detections of H1 in ELS, right? And I think one thing that's also hard to represent with this data is that even though we're showing, 1 and 2 sigma levels, right, there is still scatter outside of it with our updated model, which do match the ELS observations pretty well. So we should be doing additional tests, which involve satellite radial distribution profiles, right? So over here, we're again comparing to the Milky Way and then the Saga Gold sample because Saga Gold is complete for star forming and quenched galaxies. And overall, we're doing, again, fairly well for Saga. With the Milky Way, we're doing well from 50 to 150 kiloparsecs, but we are missing some of these like inner 20 or so kiloparsec satellites. And this is potential motivation for us to work on orphan modeling. So that way, when your payload finder eventually loses your galaxy or your subhalo upon infall, we can internally track and model those dynamics so that way we're able to push and see galaxies that are now within the losing limit of your merger tree, which will be very applicable when we want to run on, for example, TNG50, where we have been losing things at 0.5 RVIR. So some key takeaways is that we have modified Sapphire so that you can co-evolve your host galaxy and your satellite galaxies at the same time. We have added satellite-based physics to thus reproduce observations for more of our larger satellite populations. And we're setting the stage for phase 2 of our development, where we're going to add in mergers, which then lead to starbursts, and then stellar tidal stripping, bulge growth, and so on and so forth. And so that has been the satellite host galaxy coevolution extension. What about if we extend it to the high redshift universe? And this has been a very interesting question that we've been tackling for a bit of part of like this conference, because I think we can, Sapphire, great model and everything like that. All the priors and parameters and scaling relations Viraj has measured to redshift 0. If we take Sapphire and run it on this set of high redshift trees, well, 1, will it run, right? 2, do our redshift 0 inferred parameters and scaling relations hold at high redshift? And then 3, if they don't, is there room for inference so that we can infer a set of parameters at high redshift? An example over here, for example, is for our star formation recipe, where it is just the ISM mass divided by a depletion time. So it's agnostic of morphology, which is a great thing to have when we're very uncertain about the morphology of galaxies, especially at that high redshift. And this ISM depletion time is dependent on these various factors, such as this linear preterm, and then you also have a redshift dependence and a virial velocity dependence. So this is already a good question to see if this measurement of depletion time will hold at high redshifts in Sapphire. And so to do this test, we are running Sapphire on the graph 90 trees, which Aaron has talked about on Monday, and we're only evolving them on the main progenitor branch, so we're only looking at central galaxies and that population specifically. And so as a first test, I wanted to see if this depletion time formula will actually produce meaningful depletion times, right? So I've created a grid of redshift versus virial velocity, and coloring by the log of the depletion time. And then overplotted are these various contours which help guide the different values that you'll be seeing of 0.1 gigayear, 1 gigayear, and 10 gigayears. And the white shaded region, as well as that white line, are the actual data from graph 90. And we can see that we are producing pretty fairly reasonable depletion times with our graph 90 sample. And by reasonable, I mean that they're relatively physical. They're not exceeding, for example, the free fall time that you would measure in the halo. So seeing that we're kind of working out well nicely over here, I deployed Sapphire on Graph, and it ran. That's already a win. And so I've done a couple of different comparisons. This first row is looking at the star mass function for a set of redshifts, and this bottom row looking at the absolute UV magnitude using a transformation from star formation rate. And overplotted are a number of different observations, right? And you can see right here that Sapphire is very star forming. It's perhaps almost a little too star forming when you add in Aaron's comparison with the 100% star formation efficiency from his 2020 paper. And that is not ideal, but we can modify this depletion time scaling, right? So we did a quick test. What if we just multiply that pre-factor by a factor of 10? What would happen then? You basically are now going to see that we kind of are doing a better job fitting to these observations, right? So I've now added this orange line, which is, okay, you just multiplied this depletion time by a factor of 10, and with the UV luminosity functions, we're relatively better matching redshift 11 and 12, and then we're still like over-predicting for redshift 6. With the stellar mass function, we are kind of under-predicting at high redshift, but we're better matched at these low redshifts. So there is now evidence that we can modify Sapphire, specifically these parameters, right, to thus possibly do inference in this high redshift regime to thus get parameters that will better fit the data, and thus modify our star formation recipe, for example, if we want to, say, add in like a star formation efficiency term in front, or add in a possible viable reservoir of gas rather than assuming all gas in the ISM is able to be consumed. And so to sum this up, we have successfully deployed Sapphire to run on a suite of high redshift trees. We have demonstrated there is room for inference for these various free parameters using high Z observational data. And then we are also setting up possible alternative star formation recipes to be implemented in Sapphire to do other testing, as well as potentially also seeing what those free parameters would look like in this high redshift regime. And so, summary slide. Thank you for listening.
Thanks, Austen. Questions while the next speaker sits up. Questions for Austen?
Hey, this is awesome. So in the comparison of Symphony and Milky Wayist, did you see a large difference in the resulting satellite populations, and why?
Yeah, so I'm sad I took out this panel. I did show, we are looking at individual heliostellar mass functions for all of our systems, both in Symphony Milky Way and then also as a comparison to Milky Way S. And what we are seeing is that with Milky Way S, you have a larger number of surviving subhalos that are being modeled and thus have been forward modeled with Sapphire, right? And we believe that this is in part of the fact that with Milky Way S, you are forcing the fact, not forcing per se, you selected the sample of halos that do have an LMC, which may have brought in their own subhalo population with it. So I think the presence of the LMC heavily affects your subhalo population, at least with regard to Milky Way S versus Symphony Milky Way.
Other questions?
What's an orphan?
Well, not Harry Potter, sorry, bad joke. So an orphan in our context is that when so right now we're modeling the surviving satellite population. There's also the population of satellites that have been lost for various reasons, right? They've been either fully disrupted or they merged, right? But there's also a subpopulation of them where the halo finder has lost their tracking, right? And so in that case, that's what we're calling an orphan, right? Where the halo finder has lost it, but now we are now internally going to be tracking it ourselves to model the dynamics and thus the mass loss rates as it interacts with the environment. So that way, you can fully resolve, for example, supermassive black hole mergers in the context of the model, right? As well as mergers when we finally add those in as well. They're pretty theoretical, yeah.
Okay, let's thank Austen once again.